Hey y'all, so today we're going to be learning how to solve equations using logarithms. We're going to go over several different techniques that you can use to solve equations that are sort of set up a little differently. There are different techniques that you can use to solve exponential and logarithmic equations depending on how it's set up. Overall, though, your goal should be to simplify the equation as much as possible using the properties we learned in the last lesson. And so you're typically going to end up with one of two scenarios. So the first scenario is when you have one isolated function, and what I mean by that is if you have something like log base 2 of x plus 1 equals 3, notice how there's just one logarithmic function here, and so that's going to be one type of equation that you're going to want to try to simplify it to. There is another type of equation that you might have to simplify it to, and that is when you have two different functions, one on the left-hand side and one on the right-hand side. So what I mean by having the same function on both sides is when you get an equation that has the same base, okay, where we have something like log base 2 of x plus 1 equals log base 2 of 3. Notice in this case, you've got the same logarithm on both sides. Your arguments might be different, but the key thing to notice here is that the bases are the same. Now, when we solve these equations with logarithms, these are good. We're going to use a similar property to if we were going to solve a similar equation that uses exponents. So for example, like over here, if I have something like 2 to the power of x plus 1 equals 3, this is another example of a function where your exponential function is just already isolated on one side. You might have some stuff going on in the exponent other than just x, like here we have that x plus 1, but the function itself is isolated. There's no coefficients, you're not adding anything to the function, it's just 2 to some power. Similarly, you might end up with an exponential equation where you have the same base on both sides. Like if I have something like 2 to the power of x plus 1 equals 2 cubed. Notice we have the same function with the same base on both sides here, and you're going to solve this one similarly to how you solve this one. So let's go back up to the log functions and kind of go over what you need to do to actually solve it once you've got it simplified down to one of these two forms. So if you've only got one isolated function like this, you are going to use the inverse property to solve this. Okay, if your variable is sort of stuck inside the function here and you need to get it out of the function, you need to undo the function that's being done. And as we've seen with trigonometric functions and just all functions in general, the way to isolate the variable when it's on the inside is to use the inverse of that function. So that's why we're going to use the inverse property here, and what I mean by that is we are actually going to raise both sides of the power of 2. So on the first day when we looked at this, we were able to just kind of rewrite this using that inverse property as 2 to the third power equals x plus 1. And where this is actually coming from, the reason why we're actually allowed to do this is because of that inverse property, where if we raise both sides, if we use both sides as a power with the same base, the exponential and logarithmic will sort of cancel each other out. So that's what's really happening here. We've got the x plus 1 equals 2 cubed, so 2 cubed is x plus 1, and then you can go from there and solve using older techniques. I'm going to erase this exponential one real quick. So 2 cubed is 8, and we've got 8 equals x plus 1, and so here x would be 7. Similarly, with that exponential problem that I wrote down, but I just erased, I guess I'll write it over here to the side. The problem that I had written earlier was 2 to the x plus 1 equals 3. So we're going to use a similar technique here. We're still going to use the inverse property, and that is we're going to rewrite this as a log. So instead of going from a log to an exponential equation, we're going to go from an exponential to a logarithm. Now, if you know how to just rewrite it, you can kind of go straight to it. So this is my base. This is my exponent, so that's what the log should equal, and this will be my argument. So what I'll get is log base 2 of 3 is x plus 1. Now again, we're really sort of implicitly using that inverse property, which what I mean by that is, let me just kind of scoot this down, I'll erase this in a minute. If I've got 2 to the x plus 1 equals 3, what I can do is take log base 2 of both sides, and then this will cancel out and be left with x plus 1, and then we get a log base 2 of 3. So we end up in the same place. Whether or not you want to interpret it as, if you want to actually do the log of both sides, or you're just comfortable rewriting it, either way is fine, you end up in the same place. But from there, we can go ahead and solve, and this might look like, oh, well, how do we actually solve this? Well, we just need to subtract 1. That's it. It's okay to have an irrational number as part of your solution. There's absolutely no issue with that. It'd be like if you had like square root of 2. You don't want to round it or anything. You want to give the exact answer, or the exact value. So this is fine, and that's what your answer would look like: log base 2 of 3 minus 1. Now, I might ask you in some cases to give me a rounded answer, and you just type this in your calculator. So just as a quick little, let me just kind of show you real quick how to do that. Because the calculator does have the ability to do logs of different bases. Let me bring up the calculator. Let's see if I can get it to pop up. There we go. So let's turn it on. So the way you do these log bases, if I want a decimal equivalent here, is I'm going to say alpha window, and it's going to bring me up a bunch of different functions I can take advantage of. And we're not going to use, you see you got the absolute value. You've got this weird e-looking thing that we'll learn about later on. N derivative, integral. We don't need any of these right now. The only one we really care about is this log base. Okay, so let's go down, select the log base, and it's going to set up. You can see where it gives you a little box to put the base, a little box for the argument. So we got log base 2 of 3 minus 1. And I just wanted to show you at least one time how to put that in your calculator in case you don't know how to do that. So you hit enter, and you get a little decimal. So if in the event I ask you for a rounded answer, it would be 0.58, and then 4 would round up to 5. So either one is fine depending what I ask. I may not specify, but you want to be comfortable with either one, and I'll typically take either one unless I say specifically what I want. So this is how you're going to handle an equation where you've got just one isolated function, whether it's a log or an exponent. You're going to use that inverse property to rewrite the equation as the other type of function, and you should be able to get your answer from there. Now, let's take a look and see what happens if you got the same logarithm on both sides. This actually is a little bit easier because you don't have to actually rewrite anything. We're going to use the one-to-one property, which says if you have two logarithms with the same base that are equal, then the arguments must also be equal. So we can just jump straight from here to x plus 1 equals 3, get rid of both of these, and then solve. Subtract 1 on both sides, we get x equals 2. Now the reason why we're allowed to cancel this out like this is really the same reason we're allowed to do this. It is if we raise both of these as powers of 2, we'll be able to cancel those out. So that's really what's going on there. And so you're allowed to set these arguments equal to each other. You can use that same property, that same one-to-one property on exponential equations. If you've got two exponential functions that have the same base, you can set the exponents equal to each other. You are literally going to drop the base here and set the exponents equal to each other. So we get x plus 1 equals 3, so we would have x equals 2. Actually, these have the same solution here. They're set up very similarly too. We have the same function on either side, and when the arguments are different, we can set them equal to each other. This is a trick that you can typically use with all functions, not just log and exponential functions. If you've got like f of 2x equals f of 1, you can typically say that f of x, 2x equals 1 in general. So these are some of the more basic techniques that we're using here. What you want to try to do, now you're not always going to end up, of course, most equations won't be set up this nicely initially. you're going to need to use the properties that we discussed in the last lesson to simplify the equation so that it looks something like this. So you might have to sort of tweak and manipulate the equation around until it looks like one of these two before you can use the one-to-one or inverse properties. There are a couple of other types of equations you're going to encounter. We'll go over those, but most of them are going to boil down to one of these two. All right. So let's just run through some quick examples so you can kind of see how the solving process plays out, and then I'll show you some of the weirder ones. All right, so sometimes the equation is real simple to figure out, like 3 to what power is 9? Obviously that's 2, 3 squared is 9. But just to kind of give you an idea of how we want to go about solving this, you can take that and say, okay, well 3 to what power is 5? It might not be so obvious. So this is a simple case of having just one function isolated. We don't have an exponential function on this side. We could write it on this side and we kind of force it into that form because 9 is a power of 3. So if you notice that this is actually a power of that, we can write it as such, as 3 squared, and then we can use the one-to-one property to drop the bases. And so now we've got two exponential functions. We can set the exponents equal to each other, and we get x equals 2. Obviously, we already knew that. But this trick only works if this number is a power of that. So how does it work otherwise? Like, let's say if we had 3 to the x equals 5. Well, 5 is not a power of 3. So what we really need to do is we're going to use the inverse property to rewrite this. In other words, we're going to take, and this is sort of like your intermediate step. Once you get the hang of rewriting these equations, you don't really have to include this in your work. It should be implied. But what happens here is the 3's are going to cancel out, leaving you with x equals log base 3 of 5. Now, once you get comfortable rewriting this as a logarithm, you can just kind of jump straight to that. The exponent is what the logarithm equals, right? Remember, a logarithm is just a power. That's all it is. And then the base is the same, and so you're going to take log base 3 of 5 is x. If kind of moving those around and it's kind of hard for you to just memorize where everything goes, you may be better off taking this intermediate step and actually taking log base 3 of both sides and seeing how this actually does cancel out and leave you with this. Now, 3 to what power is 5? We don't really know that. Obviously, it's got to be bigger than 1, but it's got to be smaller than 2 because 3 squared is 9, not 5. This number is in between 3 and 9, so it's got to be in between the powers 1 and 2. And so it's going to be like 1 point something, just ballpark 1.5. You can leave it like this, or if you really need a decimal, you could plug that in your calculator. I don't want to do this for every single problem, but I'll do it one more time just so you can see it again how you do that. Let me move this over. So we've got log, so alpha window to bring up the log base. Going to scroll down, get that log base, and I'm just going to type it in. Now my ballpark was around like 1.5 because it's, I'm thinking 5 is kind of like in between 3 and 9. It is closer to 3 than it is 9, but you got to remember that we're not working with a linear growth here. So it's not like if it's halfway in between, it'll be 0.5. So, okay, so yeah, my 1.5 estimate was pretty close here, 1.465. Now I'm gonna kind of stick with 3 decimal places here. That's what the AP test requires. So I'm just gonna use that as my default rounding. And so that's how you're going to do that. Okay, so when you have just one function that's isolated, then you're going to use that inverse property to solve it. So let's say both of these are exponential equations. Let me give you a logarithmic one. Let's say I've got the natural log of x equals 3. Okay, there's 2 ways you can kind of think about this. One way is, if you know how to go back and forth between logs and exponential functions, it becomes pretty easy. The base here is e. Okay, so then you have to know that first of all. If it's natural log, the implied base is Euler's number here. So you've got e cubed equals x. Now, if you're wondering, like, well, how do I actually get there? What we really want to do is do something kind of similar to here where we're taking the log base 3 both sides, but we're going to do e to both powers. So we take the base here and raise both sides of the equation as powers of e. Now e to the natural log of x is just x. These two functions cancel each other out because they're inverses, and so you get e cubed equals x. Okay, so this is kind of the why this happens, but again, the more problems you work out, the better you're going to be at being able to just go straight to there. You could type this in the calculator if you need a decimal, but I don't think that's really necessary. Now let's look at a couple where maybe they're not set up with just one function, but maybe you have two functions. So let me show you another problem here. Let's say I've got natural log of 10 minus natural log of x. Well, let's just say, well, you know, let's do one more where you're going to end up with just one function. Now it looks like we got two here, but we can actually combine these. We got natural log of 10 minus natural log of x. If we have a difference of two logarithms with the same base, we can combine the arguments with division. So this would be like 10 over x equals 12. Natural log of 10 over x. And now we've got it set up where we've just got one function all by itself. On one side is totally isolated. So we can now rewrite it as an exponential equation and start to solve for x. So from here, we're going to rewrite it as base is e. So e, the power is what the logarithm equals. So e to the 12th power is 10 over x. Now from here, you just have to use what you learned in Algebra 1 and Algebra 2 to get x by itself. We're going to multiply both sides by x and then divide by the e to the 12th. And so kind of a pretty ugly solution here, but that's what it would be. So you can see this, it may not look like one of these problems where you just have one function on one side. You have to be a little careful here because it looks like we've got two, but you may, in several cases, have to use the properties we learned last class to combine your logarithms to be able to solve it. Let me show you one problem that's kind of similar to this, but that we can solve a little bit differently. So let's see here. Let's say I give you log x plus 2 log 3 equals 0. Now, I didn't write a base here, and just as a little reminder, if you do not see a base there and it says log, not natural log, but just log, then the assumed base here is 10. So I want to combine these if I can, but I don't know if I can. So I've got this 2, okay, so I can actually use a property here and move this coefficient to be an exponent of here using that power rule. So log x plus log of 3 squared is 9 equals 0. And so now I can multiply these together, or at least multiply the arguments together. X times 9 is 9x equals 0. And yeah, so now we can rewrite it. Our base is 10, exponent is 0, so we get 10 to the 0th power equals 9x. So we're just about there. Anything to the 0th power is 1, and so our x should be 1 over 9. Okay, so there's one like that. These can get a little trickier depending on what is going on in your arguments here. All these sort of boil down to solving a linear equation for the most part. But let's see what happens if it maybe simplifies down to be like a quadratic or something like that. If we have something like e to the power of negative x squared equals e to the power of negative 3x to minus 4, this is going to be a case like that second column that we wrote down, where we use the not the inverse property, but the one-to-one property. So what we really want to do here is take the natural log of both sides that allow us to cancel out the bases. So we can drop the bases and set the exponents equal to each other. So we get negative x squared equals negative 3x minus 4. As you can see, this is not going to turn into a linear equation. This will turn into a quadratic one. If I add the x squared, I get 0 equals x squared minus 3x minus 4. So this brings us back to how to solve a quadratic. I'm not going to spend a whole lot of time here going over how to solve a quadratic. If you'd like, you can hit me up in the meet and I can kind of go through some of the different techniques you can use. One is factoring, and that's going to be the most common one. If you need to, you may have to be, if this is not factorable, you might get stuck using the quadratic formula, but usually you'll use one of those two techniques. So I'm going to just factor this one. The numbers are so small, it should be pretty easy to find the factors. And what we're looking for here are two numbers that multiply to give me -4, but add up to -3. And so that'd be -4 and +1. Now, we got to be careful here because we're going to end up with two solutions here. As you can kind of see, hopefully you see where this is going. We get x equals 4 or x equals -1. Those are going to be my initial solutions. However, there are some restrictions on what x can be in logarithmic equations. You shouldn't run into any problems with exponential equations, but for logarithmic equations, you want to go back and actually check your solutions here. And it's not a bad idea to check it here as well, like even if it is an exponential, just to make sure you got it right, if nothing else. So let me pull up my calculator. I want to check the solution. So what I'm going to do here is I'm going to say e, which is right here, e to the power of, and then I'm going to say negative x squared, so 4 squared. Okay, and see what that is, and then make sure that that's equal to the right-hand side. So we've got e to the power of, this is a little tedious to type in, but what are we going to do, times 4, so my x is 4 here, minus 4. Hopefully I get the same thing on both sides. I do, so I'm all good. And then you could check -1 similarly, and you're going to find that that is also the same. With exponential equations, like I said, you're probably not going to end up with any erroneous solutions because these two functions are defined or have a domain defined for all real numbers. The logarithm does not, so you have to be a little careful there. Recall that you can't take the logarithm of a negative number, can't take the logarithm of 0, so just keep that in mind. So let's do one more. Let's say we got the natural log of x plus the natural log of x plus 3 equals 1. This is going to be a case where we do want to combine these. So we have two logarithms with the same base. We're adding them. So to combine those, we want to multiply the arguments. So I have the natural log of x times x plus 3. And hopefully you can kind of see where this is going in terms of what kind of equation this is going to turn into. We have just one function on one side, so we are going to use the inverse property and rewrite this as an exponential equation. So we're going to have like the argument equals e to the first power. Okay, so we've got x. In fact, let's just kind of take care of two things at once here. If I distribute this, then that x times x plus 3 becomes x squared plus 3x equals e to the first power. So we get x squared plus 3x minus e equals 0. You're gonna have a lot of trouble trying to factor this, especially you got this not square root, but an irrational number right here. So what does that mean? How do we solve that? Well, unfortunately, that means we got to use the good old quadratic formula. Kind of a pain, I know. You didn't want to see that, but it is what it is. Okay, so let's go ahead and actually find what that is. So x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. All right, so that's the quadratic formula there. And I can simplify this a little bit. I got x equals -3 plus or minus the square root of 9 plus 4e all over 2. And you're pretty much done here. This is not going to simplify very nicely, But what we need to do is we need to check and make sure that we're not running into problems with the domain of this logarithmic function. Keep in mind that these have to be positive numbers. Okay, so if this, this number has to be greater than 0. It's got to be positive. And this number has to be greater than 0. So if x plus 3 has got to be greater than 0, then that means x has got to be greater than negative 3. But we already know it's got to be greater than 0 anyway, so we don't really need to check this anymore. This is going to be our minimum value, or right below our minimum value. So as long as we have a positive number, we should be in the clear. If we get a negative number, that's going to turn into an erroneous solution. So we can see we've got a negative minus a positive. If we go with the minus here, this will for sure be negative. Okay, and so we can't have that, so that negative 1 is an erroneous solution. Let me actually, just to kind of clarify this, I'm going to write this out twice. One with the plus and one with the minus, so you can see what exactly I'm saying doesn't work. So there's the plus, there's the minus. So when you have this minus here, that means this whole thing is going to be negative. So this is going to be an extraneous or erroneous solution. It's going to be like a fake solution. So if we look at the other one, all we really need is for it to be positive, and then we're okay. So this number right here has just got to be bigger than 3. And it looks like it is. It's a little hard to tell, to be honest. Square root of 9 plus 4 times roughly like 2.7, but let's double check in that calculator real quick. Doesn't hurt to do a quick check. All I care about is that number going to be positive or not? So let's just type that in real quick so we can have some confidence here. I want to know, is that numerator positive or negative? It is positive, so that means that this whole thing's going to be positive. So this is the only solution. Oftentimes with these logarithmic equations, especially when you get when it boils down to become a quadratic, then you have to you're usually going to throw away one of the solutions. Just it's not like a rule, but that's usually what happens. It's possible it doesn't, so you do need to check. Don't just like throw out one and think you're done. You do need to check the other one, make sure it's not outside the domain, but this one's just fine. All right, let's look at a different kind of problem. This one looks a little nastier. Look, we've got two terms that have the same base, but look at these exponents. This one just like kind of looks a little messy. So what I want to do is show you a little trick for if your problem looks like this, meaning specifically if you've got like a 2x as one of the powers and x as another. What I'm going to do is rewrite this ever so slightly to make it hopefully make a little bit more sense to you. The only change that I might make here up front, just so that I can just kind of get my head around what's going on here, is to rewrite this first term as e to the x squared. Now I'm allowed to do that because when I raise a power to a power, I multiply the powers. So these two terms should be equivalent. Now the reason why I want to write it like that is so that I can show you a similar problem and kind of show you how to solve that, and hopefully we can use the simpler problem to figure out what we need to do here. So let's say this e to the x, I'm just going to rewrite e to the x in every instance of e to the x as u. Okay, so I'm just going to like make a little note to myself. And you do not need to necessarily write this down, but I want it to make sense why I'm doing this. So I'm just going to let u be e to the x. So basically I'm just like making a little substitution here. U doesn't really mean anything except for that it's e to the x. So everywhere where I say e to the x, I'm just going to rewrite it as u. So u squared minus 3u, right, that's e to the x, plus 2. Now, if I asked you to solve for u in this equation, it would be a little bit easier, right? Like this is just a simple quadratic. The a value is 1 here, so we can factor this hopefully. And yeah, that does factor u minus 2, u minus 1. So I get u equals 2 and u equals 1. I'm going to do that same thing over here. I'm going to factor this as, instead of u, I've got e to the x, so e to the x minus 2 times e to the x minus 1. And basically I'm solving this as though it was a quadratic. So this factoring technique can be used as long as it's set up in this sort of u squared minus 3u, or it doesn't have to be 3, but you know, you've got like a squared term-ish, a linear term-ish. Like basically if this term's power is double this term's power, you can solve it like this. All right, so let's go ahead and solve set each one of these equal to 0 and solve it. So we've got e to the x minus 2 equals 0, e to the x minus 1 equals 0. And let's take care of business here. If we're solving for x, we want to isolate each of these functions. So we got e to the x equals 2, e to the x equals 1. Notice this looks very similar to what we did over here, right? We just have e to the x instead of u. And so it is going to require one last step that this problem over here doesn't, and that is to actually isolate the x. We need to write this as a logarithm. So we have log base e, which is natural log, of 2 is x, and log base 1 is our other x. So these are going to be our solutions. One thing to notice here is that e to what power is 1? Well, e to the 0th power is 1. So we should have, this is just 0, so x could be 0 here. Let's make sure that actually checks out real quick. If I plug in 0 here, just to, e to the 0 power is 1, e to the 0 power is 1, so you got 1 minus 3 is negative 4. I'm sorry, 1 minus 3 is negative 2, plus 2 is 0, so that checks out. So here's our two solutions. We've got natural log of 2 and 0. So this technique of factoring it, it doesn't have to be e here. It could be any number as long as it's set up like this. So let me show you another one that's sort of similar here. If we have 5 to the 2x minus 4 times 5 to the x minus 5 equals 0, we can solve this the same sort of way. So again, if I want to see this as a little simpler, I can say, okay, well, let's just out to the side do a little scratch work, and let's let u be 5 to the x. If I do that, I can rewrite this as u squared minus 5u minus 5 equals 0, and so I can factor this as u minus 5 and u plus 1. All right, which would give me u equals 5 and u equals negative 1. So once I kind of understand the structure of how this will be solved, I can just go back and just replace the u's with 5 over x. Not 5 over x, but 5 to the x. So I've got 5 to the x minus 5 as one factor, and 5 to the x plus 1 is my other factor, equals 0. So 5 to the x will equal 5, 5 to the x equals negative 1. Now there is a We'll look at this in a minute, but let's look at this first. So 5 to what power is 5? You really don't even need to use the inverse property, hopefully here. Hopefully you can just recognize that 5 to the first power is 5, right? So x should be 1. All right, now if you did just rewrite it as a log, you would say log base 5 of 5 is x, but this is just 1 anyway. Over here, 5 to what power is negative 1? Well, 5 to no power is negative 1. Let me bring up the calculator again just to kind of show you why that is. If we take a look at the graph of that function, 5 to the x, just like with all parent exponential functions, they have a horizontal asymptote. So basically the graph just kind of rides that asymptote until it starts growing. It grows pretty quickly, actually, but it starts off slow. So we've got this asymptote, meaning that there can be no value that is below 0. So in other words, 5 to the x can never be negative 1. So this is not going to produce a solution. No solution on this side. We still do have a solution of 1 as a whole, but this particular factor does not generate a solution. If we were to have written this in logarithmic form, we might catch that on the back end, log base 5 of -1 is x. Remember, you can't take the log of a negative number. That's just outside of the domain. Actually, the inverse, the log base 5, is going to look just like this function, except reflected over y dx. So it goes up and rides a vertical asymptote and then curves like this. So you cannot have any x inputs that are negative for the logarithmic version of that function. So we just get one solution there. Now, we've gone over a couple techniques here. We've gone over how to use the one-to-one property, the inverse property. I showed you a couple of examples where we solved them like they're quadratics. We solved a couple where after using the one-to-one or inverse properties, they turn into quadratics. There's really just one other thing I want to show you, and I'm going to show you a couple of examples to illustrate it, and that is, how do you handle an equation where you've got two functions on both sides, but the bases are not the same, so you can't just simply drop the base. So if I have 7 to the x plus 1 equals 9 to the x plus 4, or I'm sorry, let's do x minus 4. I think it might work out a little nicer. Problem becomes, well, how do I actually solve for x here? Because I can't just cross out the bases, they're not the same. So there's two ways you can go about doing this. But let me show you there's actually a few ways you can approach this. But I like to keep things consistent. I don't want you to have to think more than you have to. So I'm going to give you, the way that I like to solve this, and see what you think. So this is a little trick you can use, and that is we can take the log of both sides, okay? And it could be any base. The base is irrelevant. I'm going to go with natural log just because, well, just from a lazy standpoint, it takes the least amount of work to write natural log than log base anything else. Even the common log, you have to write log, and this is just ln, so it's just a little shorter. Saves me about half a millisecond there. So anyway, let's take the natural log of both sides, and you're going to see why we're going to do that in a minute. Now this doesn't help cancel anything out because the bases, we've got a sort of a base mismatch here, right? Like this is Euler's number 7, Euler's number 9. These don't just cancel out here. If I did log base 7 to both sides, I could cancel it out on this side, but I'd still be stuck with it over on here. So, that will only go so far. So let's take the natural log of both sides. And again, it could be any log. It doesn't have to be natural log. That's just the one I like to use. And once you do that, you can take advantage of the logarithm properties, specifically the power property, where you can take the power of an argument of a log function and sort of just move it over to be a coefficient. So instead of having log of 7 to the x plus 1 power, we can say it's x plus 1 times natural log of 7. So that's what we're going to do here. X plus 1 times natural log of 7 equals x minus 4 times the natural log of 9. Now these natural logs are just numbers. That's just a single number times a binomial. So we do need to, do we need to do that? Yeah, we need to distribute that in, okay? And we're going to do that on both sides here. And so that's going to give me x times the natural log of 7 plus 1 times the natural log of 7, so I just have this natural log of 7 hanging out there, equals x times the natural log of 9 minus 4 times the natural log of 9. So you might be thinking this is getting out of hand here, but we're almost there. It's like 2, maybe 3 steps left. The next thing we want to do is we want to get all of our x terms on one side and all of our constants to the other side. So in other words, we want our linear terms on the left and our constants on the right. Okay, so basically what I'm going to do is I'm going to subtract this x term over to the left, okay, and that's going to effectively cancel it out on this side. And then I'm also going to take this natural log of 7 and try to move that over here by subtracting natural log of 7 from both sides. And that'll cancel out here. So basically our canceling or our reducing to 0 here is going to be this one and this one. Okay, so that leaves me with x natural log, let me clean that up a little bit. We can get rid of that calculator too, we don't need that. x times the natural log of 7, let's try to make that a little bit more legible here, minus x times the natural log of 9 equals negative 4 natural log of 9 minus natural log of 7. Now this over here is just a number. It's like 4.7, or I mean it's negative, it's not 4.7, but it's just a number, okay? It's an irrational number. You can just think of this as like just a single constant, okay? So don't get too hung up on the fact that this looks kind of funky. All right, so here's the trick. This is sort of like the whole gimmick of the whole problem, and that is once you have your x's together, you can factor them out as a GCF, or a greatest common factor. Okay, it's just like combining like terms. It's just that you actually can't put those terms together because they're irrational, so you can't simplify it. Now, once you do that, now we can divide by this factor. Now, this is just a number, so we just have, like if you think about a simpler problem, it's like if you had 10x equals 20, how do you solve that? Well, you just divide both sides by 10, right? Well, same thing here. We've got a number times x equals some other number, so we just need to divide both sides by whatever this number is. All right, so let me go ahead and do that. We're going to divide both sides by natural log of 7 minus natural log of 9. So I get x equals negative 4 natural log of 9 minus natural log of 7 all over natural log of 7 minus natural log of 9. It's not very satisfying, but that is your solution. And you could put that in the calculator if you'd like to get a number. I would, so we're dealing with the exponential here, so we don't have to worry about erroneous solutions. But if, you might want to practice putting that in the calculator just to see what you get. So that's how you deal with an equation where the bases are not the same. Just take the natural log of both sides, collect all your linear terms to one side, your constants to the other, factor out the x, and divide. Okay, you'll kind of do those same steps for any problems that are set up like that. All right, let me show you one last kind of complicated problem here. Another one where the bases are not the same. We're going to actually solve a logarithmic equation here. Okay, so this is let's see if you're ready for this one. This will be our last one for today. Log base 4 of x plus 2 minus log base 16 of x squared minus 4 equals 1. Now this one is a doozy. Okay, this is going to take a bit of writing. Make sure you've got plenty of space. I'm starting on a fresh sheet. This may take up the whole page. I'm just warning you that if you're copying this down, this one takes a little bit of work to get to your answer. It's not the most, well, I'll take that back. It probably is the most complicated one we're going to do. All right, so let's think through this. The number one thing that sticks out to me on this problem is the bases are not the same. And the second thing is I don't have the log on both sides. I've got, I can't combine these with division yet because the bases are not the same. And even if I were to move this over to the right, I got that 1 plus, so that kind of throws a wrench into things. So what I want to try to do here is rewrite these log functions so that they have the same base. And so what I need to do here is use the change of base formula. I'm going to try to make both of these have a base of 4. So what I'm going to do is I'm going to rewrite this guy as log base 4 of x squared minus 4 over log base 4 of 16. Now, if you're kind of confused on how I went from this to this, go back to, I think it was last class. In the last lesson, we went over the change of base formula, which is basically if you want to change the base to whatever you want it, in this case I want it to be 4, then it's just going to be log base, whatever you want, of this argument over log of the same base of this original base. Now this one works out nicer than some because log base 4 of 16 is something we can evaluate pretty easy. So 4 to what power is 16? Well, 4 to the second power is 16. So this denominator is just 2. So I'm going to clean this up just a tad here and say that I've got 1/2 times log base 4 of x squared minus 4 equals 1. All right, it'd be this divided by 2. But I don't really like having big fractions, so I'm just going to write it like this. All right, I do want to, now I've got the bases to be the same, so I've kind of conquered that piece of this, but the next thing to do is I want to combine these to have a single logarithm so that I can use the inverse property and basically do 4 to, take 4 to both sides power. Now before I do that, I need to take care of this 1/2. Okay, so I'm going to move this 1/2 to be an exponent of this, and this is where it starts getting a little nasty, is we've got log base 4 of x plus 2 minus log base 4 of this to the 1/2 power. So whenever you have, let me just do a little side note here, whenever you have something to the 1/2 power, that is equivalent to the square root of that something. So when I have the x squared minus 4 to the 1/2 power, that is the same thing as saying the square root of x squared minus 4. So just a little notation clarification there. All right, so now I've got a difference of 2 logarithms with the same base, so I can use that quotient property and combine these to be log base 4 of x plus 2 over square root of x squared minus 4. Now, remember at the very beginning of this lesson I said that most of these, except for like maybe those quadratic ones that we just went over, but most of them are going to simplify to a point where you just have a single log on one side, or if you have it on both, you can drop them. But if you just have one, you've got to rewrite it as an exponential equation. So I've got 4 to the first power equals this. Okay, so 4 to the first power, which is just 4, equals x plus 2 over root x squared minus 4. Okay. So from here, this is where it gets, I mean, this first part is not, like the trick here, a little gimmick here is rewriting this so that we get the same bases. So far, we're just cleaning it up. Then we use the inverse property, and now we're going to try to solve for x. And this is where most people get stuck. It's like, okay, where do I go from here? We got rid of all the logs, no exponential functions, so we really just need to figure out how to move things around here. So to do that, I'm going to multiply both sides by this denominator, which gives me 4 times the square root of x squared minus 4. Be careful, the square root of x minus 4 is not x minus 2. It's not x plus 2. This is not a perfect square, so do not, don't take the square roots of these individually. That's not how square roots work. Okay, so I do want to get rid of that square root though. That is causing the bulk of my problems moving forward. So to get rid of that, what I need to do is I need to square both sides. Okay, so the left-hand side will be, let's see, 4 squared is 16. So we got 16 times x squared minus 4. Okay, because anytime you square a square root, you just get what's left over. Those are inverses. It's kind of like doing log and exponential. Square and square root will undo each other. Equals x plus 2 squared. I'll just leave it like that for now. All right, so I'm gonna multiply. What do I want to do here? I think what I need to do here is factor these out as much as I can, and see where I can go from there. So if I factor out the left side, what I get is 16 times, and then this is a difference of 2 squared, so that's x plus 2 and x minus 2. And on that right-hand side, I've got x plus 2 squared, so that'll just be x plus 2 times x plus 2. Notice we've got an x plus 2 on both sides. So if I divide both sides by x plus 2, I should be able to cancel that out and just get rid of one of those factors. Oh, my pen's dying on me. You don't see that? This might be the end of the road for this pink pen. All right. Anyway, so these will cancel out. These will cancel out. So now I've got 16 times x minus 2 equals x plus 2. And now we've got ourselves a nice, friendly linear equation. 16x minus 32 equals x plus 2. Then just like on the last problem, flip back there, over here we collected our linear terms on one side, we collected our constants on the other side. We want to do that exact same thing here. So I'm going to collect my x terms, 16x minus x, collect my constants, so I get 2 plus 32. And so I get 15x equals 34, and we get this lovely solution of 34 over 15. I do want to make sure that this is with, I've got a log equation, so I've got to check my solution. This is a positive number. It's just over 2. So if I plug that in, let's see, 2 plus 2, that's 4. That's going to be okay. Remember, we need this to be positive, and that's really all we care about. And then if we've got something squared, something bigger than 2, so 2 point something squared, that's going to be bigger than 4. Minus 4 is still going to be positive. So this solution doesn't cause any issues. So there's our solution. I told you all this was going to be a doozy. And look at this. Oh gosh, it took a whole page. I'll try to warn you. Now, your problems are not mostly going to be this long. There might be 1 or 2 at the most that take this much work, but I did want to show you what to do when your bases are not the same. So that's it for today. Go ahead and start working on those practice problems, and I'll help you out when you need it.